Okay, this unit, we talked about objects moving in circular paths. Like, for example, this car going around on the Ferris wheel. Okay, how circular motion compared to linear motion? For circular motion, the direction is always changing, obviously. If you look out your windshield when you're driving your car around a circle, the view keeps on changing. So even if you're going a constant speed around that circle, your velocity is changing because your direction is changing. Now, whenever the direction changes, there must be a net force that causes that acceleration. We call that centripetal force, a force that keeps you moving around in the circle. More on that later. And then we call the acceleration centripetal acceleration, even if the speed is staying constant. Centripetal means keeping it in the circle. Okay, we talked about parabolas, parabolic motion, that's for projectiles. What's keeping that projectile in that curve? Well, the net force is the weight of the object for projectiles. For objects going in circular motion, it's not necessarily the weight. It can be tension, the tension in the bar right here that's holding the car on the Ferris wheel is keeping that car, that cab going, connected in the circular path that is moving. So it could be tension, it could be gravity, like a planet going around, orbiting around the sun. That force, therefore, is a gravitational force. We have a whole unit on that later. Could be tension in a string. If you got a ball, if you're holding a ball and spinning around in a circle, it's tension in a string that is a central force. If it's a car going around a flat curve, it's friction between the tires that's causing the centrifugal force. Okay, so we'll be talking about this in detail coming up. Now, when we talk about circular motion, it's very important to understand what a period is. The period is the time it takes to do one trip around the circle. The time it takes to do one trip around the circle. So the unit is seconds. The symbol for period is capital T. Not to be confused with tension. Okay, the units are seconds. So let's just practice this. Here's the second hand right here. What's the period of the second hand on a clock? Okay, how long does it take to go for the second hand to go around once, one circle? Well, it takes 60 seconds, right? Okay, so 1 minute. In 1 minute, it goes around an orbit, one circular path. Okay, so T for the second hand is equal to 1 minute or 60 seconds. Okay, what's the T for the minute hand? Okay, it goes from that 2 to around to 2 again. In how long? Well, an hour, right? or 60 minutes if you want. And what's the period of our hand, the little hand? It goes from 10 a.m. to 10 p.m. in 12 hours, right? Goes around once in 12 hours. So the period is the time it takes to do the seconds it takes to do for a number of revolutions. So, if it's one revolution, that t, little t, would be the period. Let's just do. Now, when we get to another chapter, vibrational motion, we'll be talking about cycles instead of revolutions, like one back and forth. Here's a pendulum, like a kid on a swing. One back and forth motion would be called a cycle. It's not moving in a circle. It's not doing a revolution. It's doing a cycle back and forth. But we'll save that for later. So let's do a problem with that. Okay, in this problem, a runner completes 6 laps. So he does 6 revolutions around a circle path in 648 seconds. So that's the time it takes to do 6 revolutions. I want the period. Periods of time it takes to do 1 revolution. So if you need an equation, period would be the time over the revolutions. So that's 648 seconds divided by 6 revolutions or 6 laps. So that comes out to be 108 seconds. So that's the period. Okay, next example. Takes 50 seconds. Okay, that's little t time for an object to travel around a circle 5 times, so it's 5 revs. What is the period of its motion? Okay, so that's capital T. T equals the time over the number of revolutions. So that'd be 50 seconds over 5 revolutions would be 10 seconds per revolution. But I don't write the revolution per revolution because that's the definition of period. So 10 seconds is a period. Okay, this one, runner can make a full trip around a small track in 90 seconds. Okay, well, that one full trip is 1 revolution. If you're going around a circular track. And so that is the period. The time it takes to do 1 revolution. How much time would it take to do 6 loops if you keep on with the same speed, same circular speed? So that would be period equals time over revolutions. Okay, so I'm looking for the time. So period is 90 time over how many revolutions? 6. 6 loops are the revs. So 6. So T equals 90 times 6, which is 540 seconds. Now you could say 540 seconds per revolution, but that's redundant. Next one. Object is traveling in circular motion. Its period, okay, they tell me straight up. The period is 3 seconds. How many revolutions will it complete in 1 minute? So that's little t. So you got it. you gotta be sure that the units are the same if they're shared in an equation. So 1 minute is 60 seconds to match with this seconds right here. So put that together. We're looking for how many revolutions. So big T equals the time per revolution. So I got 60 up here. Here, let's do it like this. Big T is 3 equals 60 over the revs. So, or X. So 3 times, cross multiply when you have a fraction. 3 times X is 60. So X is equal to 60 divided by 3, which is 20 seconds. Oops, did that wrong. 20 revolutions in a time of 60 seconds or a minute. Okay, so this frequency is the flip of the period. It's the inverse of the period. Okay, so I'm not going to really use the word frequency until I get to vibrational motion, like the frequency of a sound wave or frequency of light. I'm not going to do that. I'm going to call, basically, I'm going to use the word angular, the words angular speed. And the symbol for angular speed is this Greek symbol. It's a fat W. It's called omega, lowercase omega. So, angular speed for me is the inverse of period. So is frequency, but we're not talking about vibrational things that are moving in back and forth motion. So omega is 1 over period, and you know the period is the revolutions. I'm sorry, the time over the revolutions. So if we put this together, omega equals the flip of that, 1 over t would be revs per time. So basically, it's just the back is backwards. It's the inverse of a periods. I just switch these two around. Okay, the units would be revs per second. The units for frequency up here are hertz. Okay, but we're not going to talk about that yet. So you can see here that instead of talking about frequency, I'm going to be talking about angular speed, revs per second. Okay, so we'll cross out cycles for now. Okay, so we did this already. T over N is revs or cycles, which we're not going to talk about. So that's how we flip between period and angular speed. These two, period and angular speed, are therefore inversely proportional. if you increase the period, something with a big period, it has a low angular speed. Something with a small period has a big angular speed. So angular speed and omega angular speed and period are inversely proportional. Okay, so I changed this. Period and angular speed are inverses of each other, and I just crossed out the word frequency and put angular speed instead. We'll talk about frequency later again. So a motor turns 120 times in 4 seconds. So this would be revolutions. It spins, the crankshaft spins 120 revs in 4 seconds. What is the angular speed? Okay, so angular speed is revolutions per time. And so that's 120 divided by 4, which is 30 revs. 30 revs per second. Okay, in this one, as it travels around circle 50 times, so that would be the revs, 50 revs in 10 seconds. Okay, that'd be the time. What is the frequency in hertz? Cycles per second, but we're not doing that. So what is the angular speed of its motion? So angular speed equals the revs per time. So that'd be 50 revs per 10 seconds equals 5 revs per second. Okay, so instead of hertz, we're going to use revs per second. Revs per second. Now, hertz is cycles per second, but a cycle is a revolution. So again, wait for simple harmonic motion, vibrational motion for that. If a wheel spins with a frequency of 8 hertz, okay, when I say frequency, I mean angular speed. So revs per second instead of hertz. How much time will it take to spin? So I'm looking for little t 16 times, so 16 revs. So I'm looking for t. So the angular speed is revs per second. And angular speed is 8. I'm looking for the time. So cross multiply. So we're getting 2 seconds for the time. Okay, frequency is 7 hertz. That means omega is 7 revs per second. How many revolutions? So I'm looking for revs in a time of 20 seconds. Okay, so omega equals revs per second. So we got omega is 7. We're looking for revs. They gave me 20 seconds, so question mark equals 7 times 20 equals 140 revs. Okay, in this one, they give me the period. What is the frequency? So what is the angular speed of its motion? So omega equals the revolutions per time. Now, I don't really have to do this way because I know I don't have to calculate like we've been doing, because I know the period is 1 over omega. So omega is 1 over t. So all I have to do is 1 over the period is 4, so 0.25 revs per second. Or you can do hertz, I don't care. Okay, I did this one. So oxygen volume with a frequency of 8 hertz. 8 hertz is the same thing as 8 revs per second. What is this period? So you should know that period is 1 over omega. That's the equation on the equation sheet. I plug in my values. Omega's 8. So that comes out to 0.125 seconds. Okay, so it's important here to realize that there's another kind of speed besides angular speed, and that's called tangential speed. So when an object's going around a circle, it's going with constant tangential speed. And I give the symbol V for tangential speed. Okay, the velocity is not constant because it keeps on changing, but I'll talk about speed. What it keeps on changing because the direction is changing, so velocity is not constant. Okay, so what the speed is. So tangential speed is in meters per second. It's like what your speedometer would read if you're going around in a circle in your car. Okay, so here's the car going around in a circle in 4 different places on this blue circular path. And the speedometer reading is a tangential speed. And the speed's staying constant, but velocity isn't. Okay, so don't confuse tangential speed and angular speed. They're related. The bigger the angular speed, the bigger the tangential speed, but they're not the same thing. Okay, so tangential speed, it's like your speedometer reading. It's not the same thing as revs per second. So it's not the same thing. Okay, when I talk about what I mean tangential speed, well, tangential means hits the path, circular path, but it's perpendicular to the radius of the circle. That's what I mean by tangent. It hits the circular path at one point, but is perpendicular to the radius. Okay, so you know the equation. Speed is distance over time. Okay, so I'm going to use the symbol V for speed now, because it doesn't matter to distinguish between speed and velocity. I'm going to talk about speed in this unit. So the speed is distance over time. Well, average speed, but because in uniform circular motion, the speed's staying the same, the average is the same. That I don't need to put the average because it's not changing. So E equals V over T, take it from here. Okay, now if the time is the period, the distance traveled will be the circumference. Okay, so to go around once, if you start here to go around in a circle like that, you just travel the circumference, which is 2 pi r. So the time it takes to travel one circumference is equal to the tangential speed. So I should call this UCM tangential speed, not angular speed. Okay, so here in yellow, right here, is the equation that we'll be using for to determine the tangential speed, 2 pi r over the period. Here again, you have the equation, r being the radius, v being the tangential speed, and big T being the period of time it takes to do one orbit. Okay, so let's do some problems. Radius is 64 meters. He goes around once in 72 seconds, so that's the period. What's the size of their tangential speed? So what is their tangential speed? Or the magnitude of the tangential velocity would be the tangential speed. Okay, so V equals 2 pi r over capital T. So 2 pi times 64 divided by 72. I'm getting 5.58 and 5.6 meters per second. What's the direction of their velocity? Well, it's tangential to the path. Okay, so next one here, sure, tangential, so they're not talking about angular speed, but that's obvious for none. I don't have to keep on writing tangential. If you see meters per second is tangential speed. If you see revolutions per second, then it's angular speed. So I don't need to keep on specifying this from now on. Okay, so the radius is 92. How long does it take to complete one lap? So the time to do one lap is the period. So I can use V equals 2 pi r over T. V is 45. 2 pi r is 92 over the period. Cross multiply. 45t equals 2 pi 92. And then divide through 45 on both sides. And I get t equals 12.8 or 13 seconds. What is the direction of the car's velocity tangential to the path? I'm not going to keep on writing that. Okay, so for this one, it takes 208 seconds to walk around a circular track. So that's the period, the time it takes to do one lap. Speed, okay, that's tangential speed, V. What is the radius of the track? Okay, so this is very repetitive. So V equals 2 pi r over t. And so I'm going to mess around with the symbols first so I don't have to write so much. So t times v equals 2 pi r, and divide both sides by 2 pi to get rid of it. So r is equal to 280 times 1.4 divided by 2 divided by pi. I'll be sure you put pi in parentheses, 2 pi in parentheses if it's in the denominator. 280 times 1.4 divided by parentheses 2 pi parentheses. And I get 62.4 meters. What is the direction of your velocity? Again, tangential to the path, because it's tangential velocity. Okay, the radius of motion is given as r. His period is 5. His period is 5 seconds, so they tell me straight up that that's the period. What is his velocity? V equals 2 pi r over t. Okay, so let's see, 4 pi is about 15 divided by 5 is about 3. So I'm thinking it's 2.5. And I get 2.512, so I was right. Meters per second. Okay, so these are all, keep on going. Same thing. So V equals 2 pi r over t. I'm solving for t, so I'm going to cross multiply. Then divide both sides by v to get rid of the v. So t equals 2 pi times 2 divided by v, 20. So that's 4 pi over 20. It's 1/5 pi. Okay, so 3.14 divided by 5 is 0.63 meters per second. Oops, period. Units for period are seconds. Okay, so these are repetitive, so I'm going to skip a little bit. This is a trickier one, but it's good. Okay, the radius is given as 3. Its frequency, okay, now frequency, remember, is angular speed, revs per second. What is this tangential velocity? I should have said that. Because angular velocity would be 0.25 revs per second. Okay, so again, V equals 2 pi r over t. But since they gave me the angular frequency, I don't have the period yet. But you should remember from what we did a few minutes ago, big T, the period is 1 over angular speed. So basically I could replace this. So V equals 2 pi r over 1 over omega, which simply equals 2 pi r times omega, right? Because when you have a fraction in the denominator, you just invert it and multiply. So this would be 2 pi times the radius, 3 times the angular speed, 0.25. So 0.5 times 3, 1.5 pi. I get 4.71 meters per second. Okay, what is this frequency? Actually, they're asking what is this angular speed? Angular speed is 1 over t. So let's find out what t is using that equation. And so I could let's solve it the way you like. So 30 meters per second equals 2 pi times 2 over the period. So solve for the period. Cross multiply 2 pi 2 over 30. So omega is 1 over t, like I said. So omega, just flip that, 30 over 4 pi. 30 divided by 4, divided by 3.14. Be sure you put that in parentheses. Is 2.4. I get 2.38. So really, this should be 2.4. They didn't round it properly. And that would be revolutions per second, which is the same thing as a hertz if you're talking about circular motion. So these are basically the same things. Okay, is it possible for an object moving with a constant speed to accelerate? Yeah, if it's taking a curve. And when it's taking a curve, the direction is changing. So yeah, you can accelerate if you're going constant speed, if your direction is changing, like going around in a circle. Next thing we're going to talk about is this centripetal acceleration. So if an object is going around in a curve, there is a force, like I said in the very first page, there's a force that's keeping it going around. We call that centripetal force. But that's a net force. That's a net force. But the net force causes acceleration. That acceleration is called centripetal acceleration. Now, centripetal acceleration doesn't cause the object to move faster in its circle or slower. It just pulls it back towards the center of the circle, keeping it in a circular path. Okay, so yeah, you need centripetal acceleration to keep you around the curve. Even if their speed is staying constant, there has to be acceleration towards the center that keeps the car going around the curve. Okay, so if you didn't have centripetal acceleration, you would fly off on a tangent. So if this is a ball on a string, if you cut the string, that ball will keep on going in a straight line off a tangent. If this was a car taking a curve and you hit a patch of ice, no longer you had friction holding you into that curve between your tires and the road. You would slide off the road tangentially. You would, and if you ever driven up north on an icy winter day, you might experience that. So here's a question I put on a test once. The ball is moving with UCM in a horizontal circle, and the string is cut as shown. This is a top view. What direction will the ball head? So it looks like the ball is going around like that in a circle. You cut the string, it's going to go off on a tangent. Tangent is perpendicular to the radius, so that's 3. Okay, sorry, I answered this one. Okay, so what direction is the string pulling in order to keep the ball in uniform circular motion? Well, it has to be pulling towards the center of the circle, or else the blue ball would go off on a tangent. Okay, we call that force, in this case, if it's a string, we call that tension. I'll put, it looks like period, but if I put in a box, that's the force of tension. And that tension is the centripetal force. In this case, the centripetal force is that force that keeps it accelerating. So that, when I say accelerating, so that the direction keeps on changing, but the speed's not changing of the ball. So that tension is along the radius, always in direction towards the center of the circle. So this is just showing wherever the ball is, the centripetal force or the acceleration that's caused, centripetal acceleration that's caused by the centripetal force will always be towards the center. Okay, remember, the net force and the acceleration that it causes are always in the same direction. That's Newton's second law. And in this case, always pointing towards the center of the circle. So I could also draw of FC vector, which would always be in the same direction as the AC it causes. C means centripetal. Here I am forgetting to say it before I write it, as I write it. So anyway, here's the equation for centripetal acceleration. AC equals V squared over R. V is the tangential speed, not the angular speed, revs per second. No, it's meters per second, 2 pi r over t. And r is the radius, of course. So if we work this out, meters per second squared, meters per second parentheses squared would be meters squared over second squared over meters. That's the same thing as meters. So when the meters crosses out, and you'll get the standard units for acceleration, meters per second squared. Okay, again, the acceleration is perpendicular to the tangential speed because it is along the radius. The radius is perpendicular to the tangential speed. So anything that points along the radius, whether it's AC or FC, centripetal force or centripetal acceleration, is perpendicular to the tangential velocity. These are really simple, so I'll just do a few of them. car goes around a circle track radius. Let's change the color. At constant speed of 38. So that's V. What is the size of the car's acceleration? So AC. Okay, you might say 0 because it's not accelerating. The speed's not changing, but that's not what we're talking about. We're talking about the centripetal acceleration. So AC equals V squared over R. 38 squared over 82. Which I get 17.6 or rounding 18 meters per second squared. What is the direction of the car's acceleration? It's pointing towards it, towards the center of the circle along the radius. Toward the center of the circular path. Okay, I'm not going to keep on answering that question for future ones, but you should know that. Okay, sorry, I did it again. Okay, so tangential velocity is V. I use this equation. I like to play around with the symbols instead of the letters. I mean, the letters instead of the numbers. So I'm going to try to get V squared on one side, so I cross multiply. So R times A is equal to V squared. Then I get rid of the square by square rooting both sides, plug in my numbers, and I get I get 63 times 2.3. Then I square root that. I get 12.03 meters per second. What is the direction of velocity? Tangential to the curve, the circle, the circular curve, circular path, whatever. Okay, what is this period? So the period, I remember since I just found V, and I know the equation V equals 2 pi R over T. In the previous problem, V was 12 meters per second from the previous problem. So 12 equals 2 pi R over T. The radius is 63 from the previous problem. So T equals 2 pi times 63 over 12. So 2 times 3.14 times 63 divided by 12. It's going to be 32.97 seconds. So I'm going to round up. And what is this angular speed? That's omega. And you recall that omega, angular speed, is inversely proportional to the period. So that's 1 over 33, which is 0.03 revs per second. Okay, so again, AC equals V squared over R. I got V here. I got AC there. Centripetal acceleration. What's the radius? So I like to RAC. This is very repetitive. So R equals V squared over AC is equal to 2.5 squared over 5. So R is 1.3 meters. Okay, for this one, something's in UCM, uniform circular motion, constant speed, moving in a circle. Period directions of objects, tangential velocity V, and centripetal acceleration. So if you recall our pictures, there's a circle, there's an object going around the circle. There's tangential speed, tangent to the circle, but perpendicular to the radius. And there is a centripetal acceleration pointing inward to the center of the circle. So the vectors, the V and the AC, are perpendicular. I mean, you're going constant speed, but you're not tangentially accelerating if you're going constant speed. But you still have AC, centripetal acceleration, and that can't be zero if you're going around in a circle. Okay, so constant speed in a circular path type of acceleration is AC, centripetal acceleration. So once again, it's moving at constant speed, tangential speed, if it's in a circle. And if the acceleration is perpendicular, continues to be perpendicular to its velocity, then that's centripetal acceleration. They'll be moving in a circle. Okay, this is very straightforward. With a tangential velocity of 6 meters per second, so that's V. Radius is 4 meters. What is the centripetal acceleration? So just use AC equals V squared over R. This be 6 squared is 36 divided by 4. That's almost 10. So I'm going to guess it's 9. Skipping this one is the same thing. AC equals V squared over R equation. I just skip it. But you're solving for R. So I cross multiply. And then I'm solving for AC. So AC equals V squared over R. And I plug my numbers in. This one, same equation. AC equals V squared over R. Velocity, V squared, cross multiply. And so V would equal the square root of R times AC. You can solve that. Sorry, I did this without pushing a button, so here we go. So this is different because I don't have V in this equation. I'm going to still use AC equals V squared over R. But I don't have the V. So I'm going to use this other equation to find V. Okay, we've done that many times. And because this is V squared right here, I'm going to have to square this V right here. When I do that, I square everything on this side, on the right side of that equation sign. So I rewrote that. So V squared equals all that squared. So I rewrote it in that last line there. Then I substituted this with that V squared and rewrote it again. And when the r's cancels out, and so I'm left with this equation right here, which I can just plug numbers in. Okay, right here. Looks normal, except the frequency thing. That's the angular speed. That is 3 revs per second. Find the centrifugal acceleration. So AC equals V squared over R. Now be careful. The angular speed is not the same as tangential speed. So this, we're going to have to think about this one. So V equals 2 pi R over T. And again, I don't have T. I don't have T yet. So, but we've done this before. T is 1 over the angular speed. Okay, so I could substitute that T in for here and rewrite it. So V equals 2 pi R divided by 1 over omega, which is basically the same thing as you got a fraction in the denominator, so you just invert it and multiply by it. So that's 2 pi R times omega. So V squared, because I have the square right there, is 4 pi squared R squared omega squared. Okay, now what I'm going to do is substitute that in for V squared and rewrite it. So AC is equal to 4 pi squared R squared omega squared divided by R. And of course, one of the R's will cancel out. So basically, AC equals 4 pi squared R omega squared. So you plug into there all the numbers. You got the R, the radius. You got the omega. So that's all you do. Oops. Okay, sorry, that's what AC is, okay? So let's write and then put in meters per second squared at the end. I could just use that equation that we just derived, or I could start from scratch again, which I'm not going to do. So looking for the period. So now let's just solve for it again. So we got AC here. I got the radius. So AC equals V squared over R. V is equal to 2 pi R over T. So V squared, because that's what I want, is equal to 4 pi squared R squared over T squared. So I'm going to add that in for, I'm going to substitute that in for this and rewrite it. So AC is equal to 4 pi squared R squared over T squared. That's the V2 that I just wrote down. Then it's still over R. So when the r's cancels out on both sides, and so I'm left with AC equals 4 pi squared r divided by t squared. So I'm looking for period. So I'm going to cross multiply. T squared times AC equals 4 pi squared r. Then I'm going to go, I want to isolate the period. T squared equals 4 pi squared r over AC. So T equals the square root of 4 pi squared r over AC. You could simplify that, but you'd be plugging in numbers by now anyway. So it'll be 2 pi square root of r over AC. Okay? But you'd just be substituting numbers by now. Now you could write this all over with numbers and not use my symbolic way of doing the letters first. But that's your choice. I think it's much quicker. Okay, then you plug in the R, which is given up here, and the A, centrifugal acceleration, which is given up there. Yeah.
Are you doing a video right now or something?
Yeah, but that's okay. I just stopped it.
Oh, okay.
What you need?
Do you want to finish this?
You don't want it?
Well, I am full.
Okay, thank you.
Mm-hmm.
Thanks, sweetie. So, what you do to one side, you got to do the other side. So, 3 squared. Don't forget, if there's a square, you got to bring it over. Put that on top of on the numerator on the other side, and then bring the 1 over, and that doesn't. So now the AC would have to be 9 times what it was than what it was. Okay, so centrifugal force. Okay, centrifugal force is the net force is on an object moving around in a circle. And it's the force that keeps the object in the circular path that it's in. Now, Newton's second law, we'll find this out in a minute. Newton's second law of motion, net force equals ma. In this special case, Fc is net force, m is the mass of the object going around in a circle, and a is AC, which is also v squared over r. Now, that's the new equation. Fc equals mac, or mv squared over r. Okay, you need to know that centrifugal force is a vector that also points towards the center of the circle. And it's actually the force that is what keeps the thing going around in a circle. For example, if this was a car, a top view of a car going around a cul-de-sac, that force is the friction between the tires and the car, the sideways friction, keeping the car on the road. So here we have, I forgot to put that R there. Here we have what I just explained. Okay, so let's go on. Okay, once again, I forgot to turn on the button for my voice. So let me walk you through this. So they gave me mass, they gave me the tangential velocity, and they gave me the radius. Okay, what is net force? Net force is centrifugal force when you're going around in a circle. And there's the equation for centrifugal force. Plug in your numbers from above, and then work it on a calculator. I'm going to save time and not do that. And then don't forget to put newtons. And the direction of net force, this vector is always toward the center of the circle. Okay, so they gave me the mass. The net force, which is Fc, is 12.5. Here's the radius. What is this velocity? So Fc equals mv squared over r. Very straightforward. Let's solve it my way. I'm going to cross multiply Fc times r equals mv squared. I'm trying to isolate what? The v. So divide both sides by m. Get v by himself. And then get rid of the square root sign by square rooting both sides. And so I would just plug my numbers into that. And it'd be meters per second. That's the tangential velocity. Okay, you can do the plugging in solving. I'm sure you're fine with that. Here we have the same idea. We got M, we got net force, which is centrifugal force, and we got the V. And what's the radius of the circle? So Fc equals mv squared over r. Cross multiply. Fc times r equals mv squared. I'm looking for r, so divide both sides by Fc. So mv squared divided by Fc. And your answer will be in meters when you solve it. Okay? Simple. I pushed the wrong stupid button. Okay, so what did I do? First, I realized that what all my given terms were. So the mass is there. This satellite is orbiting the Earth. Here's the Earth down here. And it orbits it once every 5,900 seconds. So that means that's the special time called the period. The period is the time it takes to go around once, and it's in seconds. Okay. They give me the orbital radius right there. That's the distance between the satellite and the Earth's center. What is the gravitational force acting on the satellite that's pulling it back in the circle? Well, that is the centrifugal force. The gravitational force, Fg, is equal to centrifugal force. So I kick in the generic equation for centrifugal force. Okay, and then I realize there's no v given, no tangential speed is given. So I have to come up with it with the 2 pi over t equation because that has t in it. So why am I squaring it? Because it's squared right here. So I squared it, and I squared all the values on the other side. And that's what I have right here. I'm going to substitute it in for that guy right there. Rewrite it. This line right here. Oh, that's weird. Okay, so I rewrote it right here. But then I crossed out one of the r's because they cancel. And here's my equation that you can simply plug in those numbers. It's kind of annoying right there that they give you a big number there, but no big deal. So that being something newtons. So I solve for centrifugal force. That's really the gravitational force. Okay, in this problem, we have a ball. Here's the top view of the ball. He's going around in a circle. Here's the center of the circle. And he's spinning around in the horizontal circle. Okay, so there's the mass. Frequency, okay, that's omega, remember? Revs per second. So the string's length is really the radius. So the length of the string between the ball and where it's pivoting is the radius. What is the tension in the string? Okay, the tension, putting a capital, I'll put it into a box to show it's a force. The tension force is the centrifugal force. So that's what we're solving for. Fc equals mv squared over r. Okay, but again, I don't have the v. Phew, I gotta do this again. I don't have the v. So I'm gonna have to be v equals 2 pi r over t. But I don't have t either. I have omega. So you know t equals 1 omega over omega. I'm going to substitute that with this. And so I'm going to get v, whoa. Sorry. V equals 2 pi r over 1 over omega, but when it's like that, that's just 2 pi r. When you get a fraction in the denominator, you just invert and multiply. So b times w over 1, omega over 1. Okay, but I want v squared, right? Because that's what goes in here. So v squared equals 4 pi squared r squared omega squared. So at this point, I'm going to substitute this in for the v squared. See if it fits here. Fc equals m times 4 pi squared r squared omega squared over r. Don't forget this r here. So when the r's cancels out, leaving Fc equals m 4 pi squared r omega squared. You can plug in all the values. I don't feel like doing that. And don't forget to put newtons at the end. It's the unit. Ridiculously easy. Now, it could be friction. Centrifugal force could be friction. It could be the gravitational force or the weight. It could be tension. But in all cases, it's a centrifugal force. Ridiculously easy. Direction of that force is always directed towards the center of the circular path. Ridiculously easy. Fc equals mv squared over r. Just plug everything in. No tricks. Easy. Okay, if you know the tension in the string is the centrifugal force. So in these problems, if they give you something with newtons in it, it's probably the centrifugal force. Not always, though. At least so far. Okay, we got tangential speed. We have the radius. What's the mass of the ball? So again, Fc equals mv squared over r. And solve for mass, so when we cross multiply, then square root both sides. Oops, I'm solving for mass. Sorry. So I want to cross multiply. And then I want to divide both sides by v squared. Okay, because I'm trying to get mass by himself. Okay, so you can plug in. Okay, so here's my equation. You can plug in the values and find what answer that is. Okay, in this problem, we have an object connected by a rod. Cross out that word string. It's going in a circular path. The maximum force tension in the rod. You can't have tension in a rod. The rod can withstand is 8,500. So that's the FC. What's the maximum speed that it can go? If you go faster than this, it'll be too much of a force tension and it will snap off. The cap will snap off. So I'm looking for V. So FC equals mv squared over r. So basically, very straightforward. I'm solving for the speed. So cross multiply FCR equals mv squared. Divide both sides by m. And then square root that, both sides, so that v equals the square root of the centrifugal force times the radius, divided by the mass. And you can solve that. Here again, it's one of those nasties. Okay, and that force is a centrifugal force. That's what I'm looking for. There's the mass. There's the radius, but they give me the frequency. So that's the angular speed in revs per second. Okay, so you can change angular speed to period like we did before. They did not give me the velocity, so I'm going to have to do all this from the angular speed. Okay, velocity equals 2 pi r over t. Again, I wasn't given t, but t equals 1 over omega. Angular speed, inverse of angular speed. So I'm going to rewrite this. So it's 2 pi r over 1 over omega. But when you divide by a fraction, you invert and multiply instead. So there we go. We substitute this in for that. Okay, now I have v, but I want v squared because I have to pop in v squared. V squared is 4 pi squared r squared omega squared. So when I go back to this equation and I substitute I substitute v squared in for where it's there. Here, let's just scribble that out. Annoying. Okay, so FC equals m times this, 4 pi squared r squared omega squared over r. And so when the r's cancels out, so we're left with this equation right here. So you plug in your values and you're done. That was a very annoying problem. Okay, here for your viewing pleasure are some what if questions. Okay, so a load truck with 4 times the mass of the car. Okay, so how does the centrifugal force? I look for an equation. Fc equals mv squared over r. Okay, and then I see what is changing on one side. Okay, the speed staying the same. Okay, so the truck has 4 times the mass of the car. Same curve at half the speed of the... Oh, wait. So let's go back a little bit. Read this more carefully. A little truck with 4 times the mass of the car. So the truck is 4 times more mass. I put a 4 in front of the M. Taking the same curve. Okay, the curve stays the same at half the speed of the car. So the truck is 4 times as massive and going half as slow on the same curve. What does this do to, how does the truck's centrifugal force compare to the car's centrifugal force? So all I do, I don't solve anything algebraically. I make the left side reflect the changes that I did on the right side of the equation. So 4 times, don't forget that square there. So question mark equals 4 times 1/2 squared. So basically that equals 4 times 1/4. And basically the FC, there's no change. It's the same as the centrifugal force on the car. How about this one? So this is simple. FC equals mv squared over r. Okay, he takes a turn. I guess it's the same radius, twice the speed that he had before. How does this affect the car's centrifugal force? Well, he's going to need 2 squared, or 4 times greater. He's going to need 4 times more centrifugal force than he had before, or else he's going to slide off. So you double your speed, you quadruple the need, you quadruple the centrifugal force between tires and road needed to keep you on the road. Okay, here's just a picture reinforcing that. The centrifugal force, when you go around a flat curve, the centrifugal force is due to the friction, which is little f, the friction between actually a static friction. You don't have to worry about static or kinetic, but it's the friction between the tires and the road, the sideways friction. So right here, I'm deriving for you the equation that you use for relating the friction to the speed and the coefficient of friction. Okay, so we start out with this equation, and then we know the centrifugal force is a static friction, and there's an equation from the past in dynamics. Static friction is mu, the coefficient of static friction, times the normal force. On a flat road, the normal force is equal to the weight, which is equal to mg. So here's a free body diagram right here of the normal force, the weight, and the friction on the car. And the car's going around the circle head on, looking at it from viewing the car coming at you. You're standing in the curve, watching the car and he's about to turn to your right in this curve. He's turning to your right in this curve. Okay, now what I'm going to do is some algebra here. I equate the two equations. And you can see the m cancels out. Leaving you v squared equals r mu g. Then v equals the square root of r mu g. So that would be the maximum safe speed that you could take this curve with without sliding off on a tangent. So I will write that equation in the gold box right there on your equation sheet. Okay, so here's an equation, a problem. They give you the velocity, they give you the radius. They're telling you when you're going this 30 meters per second on this particular curve, under these road conditions, if you go any faster than 30, you're going to skid off on a tangent. You're not going to have enough centrifugal force. Okay. Determine the frictional force acting on. I don't really care about any of that. How about solving for this? Coefficient of static friction between tires and road. Okay, so yes, I do care about B. Sorry. Okay, frictional force is the centrifugal force is mv squared over r. So the mass is not given. So I can't do that. So I'm stuck. So I'm going to have to give you the mass of the car. But I wouldn't have to find that for C. Okay, so I can't solve for the friction, no force acting on the car. Okay, sorry. I don't need to find a frictional force. I can find that later if I need to. But I would need to know the mass. Okay, so let's just solve these. God, I'm just blasted. Okay, sorry. So let's solve for the coefficient of static friction. That's the only thing I really can do right now, because I didn't give you the mass of the car. So we know that V equals R mu G. Okay, so V, so what are we solving for? We're solving for coefficient of friction, so let's get rid of R and G, but first get rid of the radical. So V squared is equal to R mu G. Let's get rid of the R and G. So they get mu on one side. Okay, so that crosses out these guys. So mu is equals coefficient of static friction is equal to V squared over R times acceleration due to gravity. So that would just simply be 30 squared times divided by the radius, 175 times, we'll use 10 for acceleration due to gravity because we're on Earth. Okay, so you can solve that. It's unitless. And I get 0.51. And again, there's no unit for a coefficient of friction. So what if I wanted to solve for the friction between the tires and the road? I need the mass. I need the mass to do that. So I'd have to tell you, let's say, 2,000 kilogram car. That would have to be given. That would have to be given. So the friction, like I did up here, friction would equal the centrifugal force would equal 2,000 the mass times V 30 squared divided by the radius. Okay, so the friction is not the coefficient of friction, it's the actual friction. I get this huge amount, 10,285.7. Okay, I would round that off to probably 3 to 6 days, 103, 10,300 newtons. Okay, don't get that confused with the coefficient of friction. The coefficient of friction and friction are totally, they're related by that equation, F equals mu times, F equals mu n, or F equals n. I mean, you could solve it that way too. So it equals 0.51 times the mass, 2,000 times 10. And you get the same answer basically. That'd be 102. It's off a little bit because I'm using 10 instead of 9.8. So I get 2,000 times 20,000 times 0.51 is 11,000 newtons. So you see it's off a little bit, but and if you did use 9.8, it would be smaller and equal to that. So sometimes, let's just continue using 10. Okay, this problem, we got the mass given of the car. Here's the radius of the road. And here's the V. We'll use meter per second, not kilometers per hour. Will the car follow the curve or will it skid? Okay, well, let's find the maximum speed the car can go. And that equation is on the equation sheet. So we got the coefficient of friction when it's on a dry road and the coefficient of friction when it's on an icy road. So this is an icy road. The coefficient is much smaller than on a dry road. Okay, so let's figure out for the maximum speed on dry road. Okay, that equals the square root of 50 times the coefficient 0.6 times 9.8 or 10. Then we'll do the same thing. The maximum speed you can take the curve without slipping on icy road. So it's 50 times 0.25, smaller coefficient of friction, times 10. Now let's just figure out what those are. Okay, so on a dry road, you can go 17 meters per second without slipping. After that, you'll slip. On an icy road, you only get to go 11 meters per second before you start slipping. So if you're going 15 meters per second, you're safe on a dry road, but you'll wipe out because 15 is the maximum you can go on an icy road. I'm sorry, 11 is the maximum you can go on an icy road. If you're going 15, you will slip off of there, off on a tangent. Okay, force of friction keeps the car in the curve. When you're going around a circle, that is a centripetal force. And it's always pointing towards the center of the circle. Okay, so we're talking about coefficient of static friction, the radius and the V. So V equals R mu G. Okay, so you can go faster if the R is bigger or if the coefficient of friction is bigger. So that, okay. So let me ask you some what if questions about V equals. Okay, just what if the car was going same speed? No. What happens at maximum speed? You can take a curve. If the curve is 1/4 the radius of what it was, how fast could you go without slipping if the radius is 1/4 of what it was? Well, if I put a 1/4 there, it's under the square root sign. So you got to bring it over to the other side. This is a what if question. And square root that. So if the radius was 1/4 of what it was, and you're taking it with the same coefficient of friction, your speed would have to go to square root 1/4 or 1/2 times what it was in order to not slip off of it. So I can make a what if question out of those kind of things for the test. Here they do it. Both the coefficient of static friction and the radius of a track are doubled. The maximum velocity car. The maximum velocity a car can take a turn without slipping off. They're being pretty brief about this question. They should be more specific. The maximum velocity a car can take that curve without slipping would change in what way? So V max is. So what did I do? I doubled. Both are doubled. So R and U are doubled. So you got to do the same thing on both sides. Square root 2 times square root 2. Okay? Or square root of 4. And so that'd be 2 times V. The speed, you could take it. You can go twice as fast and not wipe out. So it would increase by a factor of 2. Right? 2 times 2 under the radical is square root of 4. Or square root of 4 is 2. Okay, I had to add this because they're being really too brief on this question. So V equals maximum speed R mu G. Now, do you see even mass in this thing? Do you see mass in this equation? No, so it's irrelevant. So change in mass does not change anything about the maximum speed. So a truck with a pickup truck that's with its rear unloaded, and a pickup truck with tons of rocks in its bed, in its truck bed, it will still, that doesn't change the maximum speed. It can go around the curve without wiping out. Okay, in this problem, we're back to going. We're just talking about centripetal force now. Okay, so so if you go half the speed that you were going before, what you do on one side, you had to do on the other side. So you're not just bringing one half over, you're bringing, because V has squared, you're bringing the 1/2 squared. So it'd be 1/4 times as much. So it'd be centrifugal force needed would be only 1/4 of what you had before. Same kind of question. So if you doubled the original speed, what would that do to centrifugal force? It would make it 4 times greater. Okay, if the curve is banked, you know, slanted, tilted like they have in highways when you're taking a turn, or on the speedways where cars race, when they take a turn, it's banked a lot. Even on a roller coaster, you can see when it goes around a turn that they really bank it the faster you're going. Because what's happening is you're getting this part of normal force. The x component of normal force is giving you that centripetal force that you need to stay around the curve without the need of friction at all. So I'm not going to drive the equation for you, but right here is the maximum speed you can take a bank curve where theta is the angle of the bank. So you don't have to derive that equation, but it's useful if you have a bank curve situation. Okay, here's some concept questions that are important. So we've been talking about speed, tangential speed versus angular speed. And we should have a handle on these by now. Now the equation for tangential speed v is that you've been using for angular speed is 1 over the period. So if I ask you some questions, here's 2 ladybugs on a rotating disc. Okay, radius 1 is right there. Radius 2 for ladybug 2 is right there. Okay, so who has the greater angular speed? Well, v equals 2 pi r over t. So maybe we should answer this one first. Who has the greatest period? Well, periods of time it takes to go 1 revolution. Aren't they on the same rotating thing? Isn't the rotating plate going around a certain time, the same time, making the same time for 1 revolution, no matter where the ladybug is? So T1 equals T2. So going back to the angular speed up here. And I don't know why I wrote this right here, because that's the tangential speed. I confused myself. So the angular speed is 1 over t. So if they had the same period, they had the same revs per second. So omega 1, ladybug 1's angular speed is the same as ladybug's 2 angular speed. Who has the greatest tangential speed? Now v equals 2 pi r over t. Now we just said they both had the same t. But if the r's different, then the v's different. So the smaller the r, the smaller the tangential speed that ladybug will have. So R1's less than R2. So therefore, V1 will be less than V2. Ladybug 1 won't feel like she's whipping around as fast as Ladybug 2. Who has the greater centrifugal force? Well, centrifugal force is mv squared over r. So whoever has the bigger V has the bigger centrifugal force. So we can use this up here, what we just said about velocity. So the friction needed to keep Ladybug 1 on the disk, the centrifugal force, would be less than the friction needed to keep Ladybug 2 on the disk. Who has the greatest centrifugal acceleration? Okay, that's V squared over R. Okay, so, whoa. So, over here, I got V equals 2 pi R over T. Which would be, if I squared V, it'd be over T squared. Okay, so, if I doubled, okay, let's say radius 2. So they have the same. Okay, so we're looking at this. Let's say radius 2 is twice as big as radius 1. So I'd put a 2 right there. Okay, so V equals 2 pi R over T. And then if I square that, be 4 pi squared R squared over T squared. And writing it like right there. Now, so if I doubled, if Ladybug 2 had double the radius, I'm just plugging numbers. Wow, this is getting messy, sorry. So if I put a 2 right here, but the period is the same, so that doesn't affect it. So really, the V squared would be 4 times more because 2 squared, because 2 squared is 4. So this would be 4 times up here. So the AC would be twice as big for Ladybug 2. Okay. Or you could do it easier. You could have done it easier way. You could say, okay, FC equals MV squared. Or let's make it easier. Probably lost you by now, but FC also equals MAC. The mass is the same for both of them. So right here, if we already determined that the centrifugal force would be bigger for the second guy, Ladybug 2, so AC would have to be bigger. But I actually figured out right here, doing it this way, that it would have to be twice as big if the radius was twice as much. Okay, so number 8, how do the centrifugal forces compare? Well, I already did that. With this work, is twice as much. The centrifugal force would be twice as much because because AC is twice as much from figuring it out here. So the mass is the same, so FAC would have to be twice as much. It's kind of tricky. Okay, this one's really straightforward. Centrifugal acceleration. AC equals V squared over R. Let's see. I don't have V. I got mass. I got the radius. And I got the period. So, you know, V equals 2 pi R over T again. So V squared equals 4 pi squared R squared over T squared. So I'll substitute this in for this. One of the R's will cancel out like we did before. 4 pi squared R squared over T squared over R. And so we're left with this right here. Plug in your values and you'll have it. Meters per second squared. Centrifugal force. I would take my answer there and multiply by the mass. So this would be 7 times the answer for number 9. For letter A, the answer for number A, I guess. What's the tangential speed? Well, I could plug it all in here. Yeah, just use V equals 2 pi R over T. I got the period. I got the radius. Okay, so that'd be meters per second. You can plug it in. What's the angular speed? Well, if I have T, it's 1 over T. So that'd be 1 over 0.8 seconds. And so that'd be revs per second, or hertz if you want. Okay, so that's the end of this first part.